This is the previous homework. This what's the word for this? Diamond. Anyway, the diamond is not just a parallelogram, and it's a more than parallelogram because the sides are equal. Okay, parallelograms is the facing sides are equal length. The facing sides are equal length. For this diamond, the neighbor sides, all four sides are equal. This is a kind of like you have a square. A square. A square is a specific of the diamond. Because the parallel, and the four sides are equal. And is a 90 degree. So if this is made of some, I'm trying to say bamboo, you squeeze it, you will get this shape. Okay, do I have something to squeeze it? I do not have. If I pour it, the two ends will get closer. The two ends will be a little further, like that. Or I squeeze it, we'll get like that. And the question is the diagonal is vertical to prove it. If this is true, then this is definitely true because this also belongs to this is a spatial. And does that look vertical? Looks vertical to me. Does that look vertical? And how to prove the two ends are vertical? By using the vector. By using vector. And I'm trying to say is including myself, and I hope you can gradually get such a thinking habit, because basically we are engineers, and we need to like to think. We need to like to think. Okay, we are not poets, writing poems. Where is the guy guitar? Last time he said he would bring guitar to the class. In order to prove this is a vertical, because I'm teaching vector, I'm teaching the dot product is 0. The two vectors, vector A and the vector B, A dot B equal to 0 if they are vertical. If they are vertical, this is a Very important. This is very important. Because I'm teaching this right now, and I give you this question right now, you know, Dr. Lee wanted me to do some the dot product thing, okay? But I hope someday in the life you see some problem. You say, oh, that could be solved by using dot product. Then that is even better, okay? Right now, because I'm teaching this, okay. Now let's see how do we make it, how do we make it that, how to prove it, how to prove it. And the, how to prove it. Do you want me to give you a couple minutes? Do it now? Okay, I stop here. I give you a couple minutes. Warm up. This is C. This is C. This is A. This is B. This is A plus B. But we want A plus B plus C. Because in your country there are three parties, not two parties. There are three parties. So A plus B. So the red one and the C do it one more time, the plus. This vector and this vector do one more time, plus. And draw this. And so this is the blue one is A plus B plus C the result. Okay, because it's C and this one. Now you can say, okay, we take this direction. Or even it's not your decision. You can predict the countries will go that way. The world. Uh, different force. Force is a vector. Force is a vector. And in any situations, not just one force. Always some people this opinion, another people that opinion. Right? Always dispute, argue, dispute. Um, so so the end is this. A plus B, okay? Another way is just A, B. This is a less joint, so most of time, this is less joint than this. So most of the time, people ready, A and B, ready. Remember? This is also the way to get A plus B. But the real original is this. It's parallelogram. You just this one and this one are the same. This one and this one are the same. And you can ignore. You can ignore this part and just look at it. This and this are the same result. Are the same result. Okay? Adding. How to do minus? How to do minus? A minus B, how to do it? How to do it? A minus B, how to do it? minus. The minus is you need to put the two ends together. You need to put the two ends together. A and B. Of my drawing. You put the two ends together, okay? And the scissor rule, A minus B. This is A, this is B, and this is A minus B. Scissor. Scissor, okay. And and if you are the president and your country, there are two parties. One people want to do this way, another people want to do that way. You want to see how different, how much different between the two, and the A minus B, this. And if it's this, if it's this, A and B, and the difference, A minus B, where is A minus B? Is here, okay? From tip to tip, from tip to tip, A minus B is here. And you can tell, say, oh, the two parties more or less are same. They have the same opinion, not 100% same, but more or less. But here, you say, wow, they are quite different. The two parties are quite different. Um, and if one group and another that, then the country is really in trouble because there's so much different. Then you as a president is really have a headache. You wish their country, they more or less are consistent. Now you see the difference. The difference is so large. The difference is so large. Okay, the minus. Okay, back to here. This is A. This is A, and that is B. After we finish this question, we take a break. This is A. This is B. What's this? This is A plus B. Okay, parallelogram. This is more than parallelogram, but it is a parallelogram. So this one is A plus B. A plus B. What's this? What's this? What's this one? Caesar. Caesar. What's this one? Is A minus B. This vector is this way, okay? A minus B is this way. If it's that way, it's b minus a. So this is a vector. Now, what's the question? The question is to prove this one and this one are vertical, right? This one and this one are vertical. And now we got the vector. This is a vector. This is the vector. We say the dot product. So this vector. So, so this vector dot this vector are they zero? Are they zero? If they are zero, then we proved this one and this one are vertical. Okay, we do it. Um, how to do it? A dot A, okay, and minus A dot B, okay, plus B dot A minus B dot B. On page 19, theorem, U dot V is the same as V dot U. Page 19. U dot V, the theorem 1.2a. Do you see it? Yes. U dot V and V dot U are the same. So here, A dot B and B dot A are the same. But here is a minus. Okay? So they're cancelled out. Agree? Do you agree? Yeah. Now, okay, these are equal. Okay, now equal. Is A dot A minus B dot B. What is A dot A? What is A dot A? Remember? Remember?
1.
1. On the next page, page 20, definition. In the middle of the page, the norm. A dot A is equal to the norm squared. A dot A is the definition in the middle of page 20. It says the norm is equal to the square root of V dot V. Do you see that?
Yeah.
So basically it's the same thing as the norm squared is equal to V dot V.
Yeah.
Do you see that? Do you see it?
Yeah.
In the middle of page 20. in the middle of page 20. It says there the norm is equal to the v dot v. Page 20, it says this. I don't know why they don't print this. They should print both. They should print both. These and these are the same thing, right? You take this square. A vector dot, again, a vector dot itself, a vector dot product itself equal to the distance square. Sort of like 3 dot 3 is what? Is what? 3 dot 3 is the 3 squared. Minus 3 dot minus 3 is what? Is what? Is absolute value squared. Is absolute value squared. Its dot itself is the length squared. So here is b dot b is the norm squared. And we said this absolute value, oops, I said wrong. The norm of vector are equal. We said this length and this length are equal because this by push is produced by the square. Okay? So this one and this one are equal. So this is what? 0. And proved. This is a Greek. Philosophers use this. When they have proved something at the end, they draw a little block. They draw a little block. I really admire those great men. So it proved this one and this one, the dot product is 0. So this and this are vertical. Are vertical. If you are familiar with this, can go very fast. I take a few minutes to drive to the point. If you are familiar, the plus minus, this can be very fast. And like you said, it's a very clean proof. So because this is a proof, so this is also vertical. It's hard if not using vector to prove the diagonals are vertical. I don't remember how to prove it if not using vector. Okay, we take a break. Anybody wants to play the 5 stone game? 5 stone game? Anybody? Nobody wants. Huh? Yeah, I can show you. Yeah, fresh our friend. I didn't bring many stones. For example, uh, you go first. You go black. Black. One. Anyway, in the beginning, maybe, okay. Now, you are trying to make fun together. Not just this or diagonal, or this is diagonal. Now right. Now I'm here, I'm blocking you, look at two. There are two there. Good, good. Now you're using some strategies. Now you are blocking my two, and you are trying to, if you put it there, then here. Okay. Right, right. You are trying to block my three, right? But actually, you already win the game. If you put a four, now if I see it now, I try to block you, you already win five. If I try to block this A, you win five. See? Yeah. Yeah, now you guys can play. Or you want, we can, we can restart. Yes. This is actually a very strong game. They can get into Olympics. Um, yeah. Good. Yeah, it's jumping. Yeah. If I don't block it, he put it there. Then, no, I have to point it. Now, if we put a four, then I can block it because of this end. How is that? Yeah. So, right. Now this one is useless. Now I'm trying you won the game. You won the game. Right. Four. Four. If I block here, yes, if I block here, right. Okay, restart. You want to play? No, what the heck? Is it a turn? It's a one. It's a one. Not there. Look at it. No, 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 no. Not there. Look there. It's a one. Okay, okay, we have to we'll play after another three. We can defend the um, okay, presidents, let's come to our linear algebra. Okay. Um, you need to understand mm, the uh, the the vector. Uh, rest is over. The rest is over. Now we page 34. Lines. 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 Okay. Um, everybody knows what a line it is, right? A line maybe is in the two-dimension flat, a line, or could be in three-dimension. Goes from there over there. That is also a line. Now, how do we use vectors? How do we use vectors to represent a line?